All right, guys. We're going to be talking about inferences for regression today. Um, and one of the reasons why this video was out a little bit late is I had to go around and pull a bunch of information because this actually um, covers information from three chapters, one chapter 26 in our book and two chapters 7 and 8 in our book that we didn't cover back when we were going through the book early on. Um, I was just following along with the syllabus, but um, it's not that big of a deal. Those two chapters, the concepts kind of build into this, so it's not going to be a big deal for us to talk about all of them at the same time. It really isn't, okay? So the calculator is going to do most of the work for us this time. It's not going to be a big deal. You guys will be okay. But what we're trying to do um, here the problem says that 3% of a man's body fat is essential fat. For a woman, the percentage is closer to 12.5%. As the name implies, essential fat is necessary for a normal, healthy body. Fat stored in small amounts throughout your body. Too much body fat can be dangerous for your health. It has some other different things on here, but they're talking about um, in order to measure body fat, it's a tedious, expensive process. So they're trying to find out if there's an easier way to find out um, to predict someone's body fat. Okay. And they're trying to find out if waist size um, can be a predictor for body fat. So they have a sample of 250 males. And what we do is we have some data here. Each one of these dots is the corresponding coordinate of a man's waist size with their body fat percentage. So, for instance, this person right here, it looks like their waist size was around 30 inches, and they have about, I would say, 8% body fat, something like that. All right. While over here, we've got an individual that's got a 45-inch waist, and it appears their body fat is about 25 or 26% right here. So what we're trying to do here with regression is we are trying to fit a line of best fit, a line that would kind of traipse right through the middle of our data here. And with the y equals mx plus b slope intercept form of that line, we would be able to input waist size, and what it would output would be body fat. Um, in order, to have a very, very, very quick calculation of body fat based on waist size. All right. So that's the concept that we're trying to work on here. All right. Now, um, as you know, we have certain assumptions that we have to go through to make sure um, that we're able to do this. The weird thing here is you're going to kind of ignore the assumptions first. You're going to run the data because it requires you to put the data into the calculator in order to see the assumptions. Definitely in the calculator because manually this would just take forever. So we're going to go through the assumptions, but do recognize that the assumptions kind of happen after you do the calculation, but before you write down or report what you have found. So first, we need to have what's called the straight enough condition. So this is called the linearity assumption. So when we look at our data plot, we want to make sure that this is obviously not nonlinear. Okay. So for instance, all of this data here is kind of somewhat you could kind of imagine a line going through like this right here. So this one meets the condition. If it just looked like there was like no correlation anywhere and it just looked like somebody basically sneezed on the screen and you just had dots all over the place, or if you had let's say some dots down here and then it started to curve or something like that, um, then you would fail this condition right here. Okay, so this is the straight enough condition. So we want our data to be somewhat, you know, linear in nature, some sort of correlation between these values here and these values over here. It appears as these values increase, so do these. So that's our linearity assumption. The second assumption that we're going to have is independence. Um, So by doing that, what we're going to do there is it says the errors in the true underlying regression model must be independent of each other. As usual, there's no way to be sure about that the independence assumption is true, but there are some things that we can think about. First, randomization. Guys, if the individuals were selected randomly from a population, then we definitely, we can meet the randomization. And also we can have the random residuals. Whenever you put this data into your calculator, it will automatically generate residuals for you, and I'll show you how to get to that. And you just kind of look and you want to see that the residuals are just kind of, somewhat uncorrelated. You know what I mean? They're just kind of all over the place. There's, you know, um, pattern, forming or anything like this. You can see that this is just somewhat completely random data. So we do pass our random residuals or independence here. Okay. The next thing we want to check is our equal variance. Um, So what we're trying to find here, guys, is we're trying to find out um, that our data has a roughly symmetrical spread. All right, what we're talking about is when you see like this end of the data, it's very, very squished down, very tight, very clumpy, where this data over here is very spread out. This would be failing that particular equal variance. One of the ways that people say this is, does the plot thicken condition? So this plot thickens over here. So since this thickens, this kind of fails. But when you look at this data here, you can kind of see that this is relatively spread out data all the way across. Yeah, there's a couple little things here and there, but for the most part, this data is kind of relatively spread out. Now, again, we're going to be getting this information for the residuals. Remember, the calculator is going to give us this, so we'll see how to get that. But here you can see the data squishing down on this side. We want to avoid clumps. We want to avoid you know, any sort of pattern here. So here, failure of the equal variance assumption, here, passing of the equal variance. Okay. And then finally, the last condition, we want this to be our data to be nearly normal. So it says we assume the errors around the idealized regression line at each value of x follow a normal model. We need this assumption so that we can use students' T model for inference. As we have at other times when we use students T, will settle for the residuals, satisfying the nearly normal and the outlier condition. So we're going to look at a histogram of the residuals, and it should be somewhat unimodal, all right, and symmetric. And so this here passes that. If you see like some outliers that are like way out to one side, if you see like a peak over here, then it settles down, then another peak over here, um, that would be a failure. But here, this one passes for us. Okay. And as I said before, guys, what's going to come first, the conditions or the residuals? Guys, as you go through the question, you're going to be, running some of the calculations before you meet the assumptions. Um, that's the only way to get the information. Here it says we get the residuals only after we compute the regression analysis. So, for instance, you're going to put this in your calculator regardless of what you notice. You're going to go ahead and run it. And then if you notice as you go some issues, you can bail out. So here it says first, you're going to make a scatter plot of the data to check the straight enough condition. Um, then you're going to go ahead and fit the regression line, find the predictive values and the residuals. You're going to make a scatter plot of the residuals and take a look at those and make sure there's no pattern. You're going to check for any kind of bend, thickening, thinning, outliers, different things like that. Um, if the scatter plots look okay, you can make your histogram of the residuals, check the nearly normal condition, and then everything's okay, then hey, go right ahead. If at any point you're going through there and you notice anything that seems, you know, definitely off, that's when you're going to stop and say, well, I couldn't meet the conditions in order to, complete the analysis. All right. A couple other things that we need to worry about when we're doing this. One, standard error of the slope. Recognize that your slope is not going to be perfect. When you've got data with, those plotted points all over the place, there is not going to be any perfect slope. for that line. So a couple things that go into that. Spread around the line. For instance, some of the points will be further away from the line than others. Spread in the x values, that will be, left to right. That's x, all right? The sample size, the more, bigger sample size, it should produce um, less standard error in the slope. I'm going to show you how to get this in your calculator because, again, it says you'll probably never have to do this by hand, but we'll talk about how to get this. One thing that's a little bit different here, we have n minus 2 degrees of freedom. All right, so uh, before there was 250 males weight and body fat in our data. That means 248 degrees of freedom. And the reason is, remember, we have two different variables. So it's normally n minus the degree, the number of variables. Here we're dealing with two variables. So, that would be the x variable that's moving left or right, let's say uh, waist size, and the vertical variable, the one that's moving up and down, um, body fat. So that's n minus 2. And the one that we're doing in a few minutes, I think there's 11 data points. So that would be 9 degrees of freedom. I think one of them is temperature and one of them is time. So if you know, take those two variables away, you get your n minus 2. All right. And the null hypothesis, this is the only thing I really wanted to show you right here, is the null hypothesis in a t-test for regression is that the true slope is equal to 0. All right. So think about a 0 slope. That'd be a horizontal line. And basically what we're saying is, remember, the null is usually nothing exciting is going on. Nothing's really happening. Things are just what they are. Well, a slope of 0 would say that y doesn't tend to change linearly when x changes, so that there's no real association between the variables. So our alternative hypothesis is going to be that they do have something to do with each other. All right. So we'll see how that goes. We're going to get a p-value when we do these as well. And we're also going to see how to do a confidence interval for these at the same time. All right. So here is a one that we're going to do and that I'd like you to try to do on your calculator. This is the data that we're going to end up putting into our calculator right here. You're going to see me doing that in a few minutes. And then I'll just kind of walk you through what you have to do to get this done. That's what they're doing right here. If you want to pause on any part of this video so that you can see this, because you may not have your textbook. This is located on page 717, by the way. It's not that big of a deal, but I'm going to run you through one of these right here. Okay. All right, guys. So what we're going to do here is we're going to see how to do that TI tips from page 717, and you can use this as kind of like a model how to do the question about the burgers and the question about the Toyota Corollas. Okay. So the first thing that we need to do, of course, is enter our data into our lists. Okay, so we're going to go to stat, and we're going to go to edit, and we need to drop our data in. So our data for our first point here is going to be degrees in Fahrenheit. So we're going to do 44, enter, 46, 47, 50, 51. And what we're trying to do, by the way, here, guys, is we're trying to figure out if there is a correlation between the air temperature and performance for women's marathon, or some sort of women's track event. I don't know if it was marathon. Let me take a look at this. Yeah, it's marathons. So we've got 11 points of data. So these are all temperatures that, in the race. We're going to go over to list 2, and we are going to put in, I guess these are finishing times, 142.7 minutes, 142.1 minutes, 143.8 0.4 minutes, 143.6 minutes, 144.0. So I'll just, oops. It's messed up. Okay. 144.0, 143.4, 142.4. By the way, you'll get an error if you don't have the same amount of data in each one, so make sure that you have 11 pieces of data in each one, or if you're doing a different problem that it matches up. 3.4, and then one more, 143.4. Okay, so we've got the same amount of data in each one. All right, 11 entries. Right. So the first thing we're going to do, again, this is the weird part, is we don't check our conditions right away. We're going to go ahead and we're going to go ahead, we can check the straight enough condition. We can do that one there. So we want to check the straight enough condition. We can quit out of this, just get back to the original screen. We didn't get rid of anything, so I just hit second quit to get out of this. And in order to do our stat plots, what we're going to do is, to see our data, we're going to hit second stat plot, and we want to turn plot 1 on. Remember how to do this a long time ago. All right, so we're going to turn that on, and we're going to do a scatter plot. That's that first one right here, scatter plot. And our two lists are list 1 and list 2. That's where we put our, our information in. And then, so everything's in there. We got everything we need. So we're going to hit second. I'm sorry, not second. We're going to hit zoom. Oops. Zoom, and we're going to go down to zoom stat. Now, remember what zoom stat does. Zoom stat kind of sets this window automatically to the data that we've entered. All right. So our X data went from 44 to 65, and our Y data went from 142.1 to 144. All right. So it's automatically going to set our data for that. So we can hit zoom stat, and there we go. This is our data. So this is where we want to look at it and do our, straight enough condition. Now, again, I know the data kind of looks a little bit off, but you can kind of see a little bit of a, doesn't have to be a perfect correlation, but I think you guys can see that we could possibly make a line go through here somehow that's going to, somewhat fit our data, a line that goes through the middle here. So basically, if it's just not completely all over the place, you're going to do this anyways. All right. So, we've met our straight enough, uh, condition requirement. All the other conditions that we have to wait until we get our residuals. So we have to do the math anyways. All right. So here is how we run the math on this. So what we're going to do is we're going to go to stat, and we're going to go to tests. And what we're going to run is a linear regression t-test. So we're going to just go down the list. We're going to find lin reg t-test. There's another one there too. I'll show you that one while we're here. So we got two, lin reg t-test and lin reg t-int. We are going to actually end up running both of these tests. But the first one we're going to do is the lin reg t-test, and we're going to hit enter. All right. So it's asking us what values do we want for our X list, our X values, and that is our list 1. What values do we want for our Y list, that is list 2. It's asking us frequency, that's always going to be 1. And then it's going to ask us right here, basically what kind of tailed test do we want? Do we want to find out if it's less than, greater than, or if it's not equal to? What we want to do on this one is we want to use the two-tailed test, not equal to. So the question that we're answering this time is whether temperature hinders or helps performance in a marathon. So if we were just trying to figure out if it would help, we might do one of these other ones. But since we want to go either way, we're going to actually do this one right here. Now, here that says regression equation, you can enter that in if you want, but it will automatically enter this in for you with a couple key presses. So that's what we're going to do. So when it says regression equation, what we're going to do is you are going to hit vars, and then you're going to go over to the Y vars menu right here, Y vars, and just click on function. We want to enter a function in there. Enter. All right. And then it's going to drop that into Y1. So we'll hit enter right here. So it actually, it's going to say, hey, put the regression equation into Y1, basically is what it's going to do. So then we're going to go down to calculate. All right. And it's going to produce a bunch of data for us, almost all of the data that we need. There's just one piece of data that we don't get, and it's super easy to get. So it's not that big of a deal. So the first thing we have, it says y equals a plus bx. This is, again, this is kind of like mx plus b, except they just kind of rearrange it a little bit. So we get a t-score. All right, remember t-score is kind of like a z-score. It's just helpful with lower numbers. And notice we only had 11 pieces of data, so z-score would not be appropriate. So t-score, we get our p-value, which is 0.285, which is kind of a big p-value. We get our degrees of freedom, which is 9. That makes sense because we put in 11 pieces of data, and it's n minus 2. So 11 minus 2 is 9. We get our a value. This is our, again, this is our y-intercept, basically. We get our b, which is kind of like our slope. And another thing, it's called our regression coefficient. It's the slope of our line, basically. We get s, which is our standard deviation of errors around the line. It's just basically telling us how close our points are to our line. All right. And it's even saying, hey, you got some more information. So we can press the down arrow. We get r squared. R squared is something, it's the variability explained by the model. Let me explain what that means. An R squared of 0 means that none of the variability in the y is explained by the model. All right. And an R squared of 1 means all of the variability in the y is explained by the model. So this is a value you do want to look at, R squared. We also have more data. We have an R value. This is the value that got squared to make this. The R is the linear relationship. If this number were 0, that means there is no linear relationship in the data. If this number is 1 or -1, that means it is perfectly linear relationship. So with 0.35, they're just basically saying how closely the line follows the data, basically. And here you can see our graph, by the way, and it did put that in there. And of course, we could see that by hitting our little graph thing here. It's going to show that line there if we did that. So you can see there's a bunch of information that we got out of this. Now, one piece of information that it did not give us is the standard error, okay, which looks like this, SEB, okay. Actually, there's usually parentheses around it. Now, that's easy to get from this data, though. This T equals B divided by the standard error. And if you notice, these two pieces of information are given in our data. So here we've got T, and here we've got B. So if you were to rearrange this, think about it, you can put this over 1, and then this becomes a proportion. And if we switch these two right here, all right, so that means the standard error equals B divided by T. So if we take this value here and divide it by this value here, it produces our standard error. So basically, standard error equals about 0.0325, let's say, divided by 1.13, let's say 6, because of the rounding. And so this value here would produce our standard error. So that's one of the only pieces of data that this calculator does not give us, this linear regression t-test. Okay, now we are going to do a little bit more. All right, so first we want to see how to do a confidence interval. All right, so we're going to do this same, use the same exact data, but now we're going to, instead of running the linear regression t-test, we're going to run the linear regression t-interval. Okay, so we're going to go back to stat. Move my pen out of the way here. Go back to stat and tests, and we're going to go down to linear regression t-interval. My computer's being very slow this morning. All right, linear regression t-interval, option G. We hit enter. And it asks us again what data to do. The only other thing we got to pop in here is what is our confidence level. We're going to do 95%. That's the most common one. So we're going to go ahead and calculate that. All right. And so we get some of the same information that pops up, but it also gives us our interval right here, our t-interval. All right. So we can say with 95% confidence that between negative 0.322 and 0.9728 is our confidence interval for this one right here. And then the other thing that we need to look at is we need to check our residuals now. Here is weird because, again, we normally check our conditions early on in the problem, and if we don't meet the conditions, we don't do the calculation. Here, we really couldn't check the conditions until it actually, ran the calculations in order to drop those residuals into our calculator. So now we're going to look at the residuals. Whenever you put the L1 and L2 data into your calculator, it automatically created a new set of data called residuals with the name of RESID. All right, so we're going to take a look at that. So we're going to make a plot from that. So we're going to go back to second stat plot. We're going to turn this data off so that we don't have to worry about it messing up our view. We're going to turn first, this is our real data. We're going to turn that off. Okay. Then we get out of that. Go back into stat plot. We're going to turn plot 2 on. We want it to be, scatter plot. We want the X list to be the same, but we want to change this list. We're going to clear that list. And in order to get to the list, we're going to go to list. So second list. And then we're going to go down and look, hey, there's our residuals. We're going to go down here and say, hey, we want this data to be used. All right. And so we're going to go ahead and hit zoom stat. For this new data, we want to make sure this new data is in the window. And there we go. Guys, these are our residuals. So again, what are we trying to figure out? We're trying to figure out if these are clumped in any kind of way. And it doesn't appear to be. I mean, they appear to be somewhat spaced out, kind of haphazardly. That's our data, from that. And then the last thing we want to do is we also want to check that in a histogram version to make sure that we don't have any crazy outliers. It's somewhat symmetrical, somewhat unimodal. So again, we can go back to second stat plot, and then we can just go back down there, and we're going to change that to a histogram. Okay. And I think we can just go ahead and graph it. Well, actually, I think we may have to change our zoom stat. All right, there we go. And as you can see, our data is somewhat, somewhat unimodal, somewhat symmetric. Don't see any crazy outliers or anything like that. So there we go. All right, so it meets the conditions. Now, what in the heck did all of this mean? Okay, if you remember our p-value that we had, our p-value was 0.28. That's a pretty big p-value. If I could get back to that to show you stat tests, and it doesn't matter which one of these um, we do, whether we do linear regression t-test or linear regression t-interval, both should show up. But I'll just do the t-test. All right, let me scroll down here really quick. So our p-value is 0.28, guys, 0.28, 0.29. So with a p-value that big, you know, it appears that temperature does not really have much of an effect on performance for marathons. And I believe all of these were women's marathons. So what it says in the book. So it appears that there doesn't appear, there's not really a correlation going on there. So even though we can fit a line to it, and it meets all the, all the assumptions and conditions and all that other kind of stuff, it just doesn't appear to be much going on. If our p-value was much, much, much smaller, yeah, there would appear to be something going on there. All right, and we would, we might be able to say that there does appear to be a relationship between, like maybe the burgers, calories, and fat content, or the Toyota's value versus their age, as a couple of your problems are. But in this problem, it appears that there is not, much of a correlation. The work for this week does bounce all over the book. That's why I'm only giving you guys one assignment this week, not two. So we've got some work from chapter 7 and some work from chapter 26. So I'll go ahead and put those up here on the screen. Yes, this is 6 problems here, 7, 8, 9, but these right here are super fast. So, right, the first 2 here, again, I'm not going to go through these. You can just pause on this screen. Next 3, number 6, the last one from that first section. Then you got one that actually is going to be very similar to the one that I'm showing you, where you actually have to put data into the calculator. So here's your data on fat and calories. And then down here, we've got the answers that you need to find, questions you need to answer. All right, and then number 24, it's about some Toyota Corollas, trying to see if there's a correlation between age and price of a car. Again, pause this if you need to. I think I got all of the data on one screen at one time there. Make sure that you clear out all of your old data in the calculator before you put this new data in there. There is the questions you need to answer. And then the last one is where you're actually using some of that data in order to get a confidence interval and to explain it. All right, guys, have yourself a great week.